we left this device in vacuum for 7 days and remeasured it, and we found that the pinch-off voltage shifted, actually by quite a lot, by about 15 volts. But the on current stays basically the same. After exposing that sample to a further 60-second oxidation, the threshold voltage actually moves back to around 0. And then if we left the sample in atmosphere for up to so far up to 20 days, we're continuing this measurement. We'll measure it again after 40, 50 days. But after this subsequent oxidation, it actually became very stable. So it's telling us really that we need to perhaps reach a threshold in the doping concentration to get a stable device. But once we do that, we do get very stable behavior. And another way, really, just to quantify the quality of our devices is to measure the contact resistance. Before and after oxidation, the red bars are after oxidation, and we see that they're a lot lower. So again, we're achieving much lower contact resistance by this oxidation process. Okay. So the previous slides, I've really just talked about one measurement technique, which is to change the carrier concentration, change the gate voltage. Here we're going to use another tool that's available to us, and that's to change the source drain bias and just do these IV sweeps. Before oxidation, if you measure the device at low temperatures, you basically see a flat region around 0 DC bias. So this is indicative of tunnel behavior. So we're at low temperatures, you've removed the thermionic emission part, you've removed the thermal energy from your electrons, so they can't jump over your tunnel barrier. It's only when you go up to higher bias that you start to get a current flow. So that's one key thing to notice from this. The other key thing is that it's asymmetric. So it's telling you that your contacts are either the contact resistance isn't symmetric, or you've got different levels of doping in your channel area. It's just an asymmetric, non-uniform device. If we then measure the sample after the oxidation process, this is at 300 Kelvin, so basically room temperature, sweeping the gate for different gate voltages. At the largest bias here, we can see that it's still not symmetric, but the current has increased significantly. Here we're looking at nanoamps. After oxidation, we're looking at microamps. What we'd like to see is a nice straight line, which is what we know as ohmic contact behavior. And so we just repeatedly exposed the sample to oxygen plasma 60 seconds at a time, and we found that after 180 seconds, so 3 times oxidizing this wafer or this device, we get this much more linear trend. Now there are several reasons, possible reasons for that. One is you've reached a sufficient doping level. The other is if there's any directionality associated with the oxygen plasma process, then remember that you've got these etched holes. So any directionality at all will mean that some regions are going to be missed during the oxidation process. So by putting it in several times with random orientation, then we get a much more uniform doping in these hole areas. Now we found one thing that supports that really is at our second sample, we just oxidized it for 180 seconds straight away. So because we thought perhaps 180 seconds was sufficient to give us this a high enough doping concentration. But the IV sweeps turned out not to be so linear. So we exposed it to a further 60 seconds to get this more linear trend. So again, it's supporting this directionality idea in our oxidation process. If we take the same data, exactly the same data, and plot it in this form, so your y-axis is this log, natural log current divided by bias voltage squared as a function of 1 over the bias voltage, you see this trend here. And we do that because at low temperatures, your current through a tunnel barrier is described by these two equations, depending upon whether you're in the low bias regime or the higher bias or Fowler-Nordheim tunneling regime. According to this formula, if this becomes your y-axis, this becomes your x-axis, this is just a constant. So for each device it will be different, but it's for every device it will be, for a single device it's constant. And it depends upon your channel width, which is this d, and your channel height, which is this phi. So we can use this data at the lowest temperature, take the linear part of this curve and really estimate what our width and height of the barrier is. We find that after oxidation, barrier heights around 300 and widths from 0.3 to 0.7. Before oxidation, barrier heights are reasonably similar, same order, but the barrier widths are much bigger. So it's telling us that our oxidation process is giving us more control over the barrier width rather than the height. Now, the last sort of experimental data I'm going to introduce to you is to do with hysteresis and trap density. So one very special characteristic of these devices is that the hysteresis is very, very low, and it's temperature independent. Now, that's quite remarkable because hysteresis is caused by trap sites, and you'd expect temperature to affect the rate at which those trap sites are filling. So the fact that you don't see much of a difference over such an extreme temperature range is telling you that your trap sites aren't that many. Now, if you compare, so this is our sandwich structure compared to our control structure of WSC2 on silicon wafer, we see that the hysteresis here is quite big, and we can compare the data from those two plots here just by converting the difference between the forward and backward sweeps to a trap density using the capacitance formula. And here we see for our encapsulated devices, much lower and temperature independent trend. Now, if we think about mobility as well, that's a further way of characterizing transport. In our control device, we see a trend which is consistent with variable range hopping. So to get hopping, you need a certain amount of disorder. Whereas in our encapsulated devices here, we see a trend where the mobility actually increases at lower temperature. And that's a trend that we're quite interested in, and we're currently researching further to further understand the transport characteristics in this case. Now, just to summarize, there are a number of firsts in this work. That is, it's first to combine these transferred contacts with the selective doping, and we can control precisely the doping location, area, and density. We protect the channel, which is very important. We achieve threshold voltages which are very close to zero, and that appears to be quite consistent in all of our measurements, and it's very intriguing and worth investigating further. And we create very stable devices that we can leave in atmosphere, and they're safe for multiple days. And with that, I'd really just like to thank the people who are responsible for this work. So the students, without them, this work would not be possible. So I am very, very grateful to them and to the funding agencies and for the opportunity to give this talk. And thank you for your attention.
Thank you, Luke, for your interesting talk. So now it's time for question. Yeah, please.
Thank you for the very nice talk. I have one question. I think the oxidation process is very interesting. And I'm wondering, do you have any idea how much of the, for your 2D material is actually, I know you have illustration indicating the very top being oxidized, but I'm wondering if you have better knowledge about how much is actually being influenced, and also if you introduce more, for example, you do the plasma for longer, will it